Alright, hey students, and welcome to the next presentation, which is on resistance and conductivity. So the syllabus points we're covering here are essentially just what resistance is, the idea of what's ohmic and what's non-ohmic, and then we'll also look at Ohm's law, which is that guy there. So in a nutshell, electrical resistance is the same concept as, friction or air resistance. So when these electrons want to start moving in a conductor, they're met with resistance in the form of vibrations within the structure of the conductor or whatever. When they have resistance, they will struggle to get through it, and by struggling to get through it, then the amount of electrons passing through the conductor every second will decrease. In other words, they will make the current decrease. So if we tie that together with everything that we've learned, first let's look at this diagram here, which is the water analogy. So if we have a water tank, which represents the battery with all its charges in it, and the potential here, that is our potential for the water to fall, or in this case it's going to be flowing through a pipe downstream. So this potential is produced by putting it at a higher point, so a higher gravitational potential. In this, for a battery, that potential is produced in another way, usually like through chemistry. And then we put a pipe in place that allows that current to flow, and that's what you're looking at here. Now, for the water analogy, resistance can be seen as the thickness of that pipe. And also, you can also say it's not just the thickness of the pipe, but it's also the sort of the length of the pipe. If you try to drink from a very long straw, you know that it's more difficult to get the fluid to move through that straw. So electrical resistance is effectively the resistance for that current to flow. And recently we've seen more versions of this sort of diagram. This is one that I've just found this year. I usually use something a little bit different, which demonstrates the relationship between the current, the voltage, and the resistance. So you can see that you've got volts being that pressure of pushing that current through, which is the amps, and the restriction on that, or what tries to prevent that current from going through, is the electrical resistance. Something that you're going to be becoming quite familiar with during the course of your physics is what we call Ohm's law. And there was this scientist called, now it looks like George, but it's not, it's Georg Ohm. And he found that the current that flows through a circuit is proportional to the voltage. In other words, if we go back to this diagram here, you can see that if volt over here was pushing harder, then you would know that more current would go through. So effectively, what he found was that the more voltage you have, the more current you have. And then there was this ratio of voltage divided by current. So the higher the resistance, then the less current you would have for the same amount of voltage, which makes sense back to that water analogy. If you make the pipes really, really skinny, but you kept the potential the same, then you would have less current flowing through those pipes. So this is the formula that you would need to use to apply this a lot. So when you are looking at circuits, let's say we have a battery here, and then that runs through a resistor. If you know the voltage across these 2 points, so if you know the voltage applied or the potential difference across the resistor, and you know the current that's flowing through that resistor, then you can determine the resistance of that resistor. Or if you know the resistance, you can determine the current that should be going through that circuit. And we'll look at that more closely when we're looking at circuit analysis. So there's not too much complication when it comes to the calculations. So you just have the resistance being equal to V divided by I, and what you see a lot of it is actually V equals IR. And obviously we can just find out I by saying V on R. So these are the three variants of that. You sometimes see this triangle as well. That might be helpful. But with that equation, is it possible for you to determine these unknowns in the circuit? So pause this and give these a go. So for part A, it's just asking for the resistance of the wire, and we know that the resistance is equal to V on I. Now this version of the equation is the one that's in your formula sheet, so it shouldn't be too tricky to get to. And that's equal just to the 16 volts divided by the 2.4 amps. Now keep it in volts and keep it in amps, and your resistance will be given to you in ohms. And that should be 6.7 ohms. Okay, and the second part is saying, well, what is the potential difference needed to make a current of 3 amps flow through the wire? So, in other words, we've got this, say we've got a battery and we've got this wire, and what it's saying is when you apply 16 volts across these two terminals, or if you have a 16 volt battery, then the current flowing through the wire is 2.4 amps. But if we want 3 amps to flow, what potential difference do we need? So we're just going to be rearranging that equation. So that's part A. And part B is just saying V equals IR, which is going to be 3 amps multiplied by the resistance. The resistance is 6.7 ohms. Now, we are making a big assumption here. We're making the assumption that the resistance of the wire is going to be constant regardless of the voltage. So if we just, that should end up being 20 volts. So that assumption that we make, that the resistance stays the same, that the component is what we call ohmic. So when it's ohmic, it has a constant resistance regardless of what the voltage is and the current going through that device. There are many components out there that are non-ohmic. A light bulb is a really good example, but we'll talk more about that shortly. Now the units for resistance are ohms, so it's that capital Omega. So just to recap, your voltage is measured in volts, your current is measured in amps, and your resistance is measured in ohms, and that's a terrible ohms. Let me try that again. There we go, that's better. So what is it about a material that gives its resistance, or a wire? So what makes this wire 2 ohms and this other wire 4 ohms? So there's 2 factors that really come into it, and that is sort of the resistivity of the material, and that's an intrinsic property of that material. And there is an additional thing that sort of comes under resistivity, and that is temperature. So the resistivity of a particular material actually depends on its temperature. So you have the material itself and its temperature will affect that. And we talked about how current is the flow of electrons, and I've already shown you this diagram in a previous presentation, that when those electrons are flowing through, they're not going to be traveling in a perfect straight line and avoiding all the obstacles in front of them. But if we cool down that wire, if we cool down that material and we make that lattice vibrate less, then there's an easier path for those electrons to flow, which means that we decrease the resistance. Now, I'm just going to point out now that, which is probably something you've already figured out, that the resistivity is the opposite to conductivity. So if something conducts electricity really, really well, then we say it has a very low resistivity, and vice versa. So just something for you to think about before we move forward. Do you think that the resistance of an object depends on the path that the electricity takes through it? So what I've got here is a rectangle, and it's a rectangular conductor. So let's just say it's a slab of copper or a slab of aluminium. And if we connect wires on the long side to a battery, and we also connect wires to the short side, is the resistance the same in both cases? So looking at the diagrams in front of you, do you think that the current will be higher in this one, in A, or in B? Or do you think that the current that flows through the circuit will be the same in both cases? Have a think about that, and then we'll move on. So the resistance depends on the path taken. We know this. And you can see that in this first part, in part A, it's a longer pathway for the electrons to flow. So if you, similar to a water pipe, if you add more pipe onto the end of your sort of circuit, then you can expect that there's going to be more resistance. So you'd expect that the resistance in A would be higher than the resistance in B, be lower. So effectively, the current flowing through B will be higher because it has a lower resistance. This formula used to be in the syllabus, and you still will see it, and it may even be, you might find it in an exam, especially in the comprehension section, and that is looking more at the relationship between resistance and resistivity. So resistance is what you definitely need to know, and like I said to you in an earlier slide, that depends on that intrinsic property of the material called resistivity, and which also affects temperature. But if you have a wire, and you have a wire made out of a particular metal which has a resistivity, is there a way that you can determine what the resistance is going to be? And the answer is yes, you can, and that's this formula here. So effectively what it tells us is that the resistance is equal to the resistivity, which is what you'd expect, multiplied by the length of that wire. So the longer the wire, the higher the resistance. and then divided by the cross-sectional area of that wire, which can be seen as the thickness of that wire. So if I were to draw two wires, so if we do it close up, so there's one wire, and then I draw, it's not a terrible drawing, another wire, and you can see that it's a thicker wire. Then, as you'd expect with the water analogy, you're going to have more water molecules flowing through this wire, so you can expect that because it allows more water to flow through it, it's going to have less resistance. And that's why area, so the cross-sectional area, if you know your maths, is the area of a cutout through, so it's this area here. So the bigger this area, then the more current can flow through it, so the less resistance that wire has. And the longer this wire, which is this feature here, and the longer that feature, then the more resistance you have. And that leads us to finish with this equation here. And just to finish, and we'll do an experiment on this, we'll be looking at the property of an ohmic versus non-ohmic resistor. So we've learnt that the resistance of something is equal to the voltage divided by the current. Now, if we measure the current flowing through a wire at say 2 volts, and then we increase it to 4 volts, what this equation tells us is that if we double the voltage across that wire, and then we will double the current, which makes sense. And if that happens, you end up with what's called an ohmic resistor. And an ohmic resistor is this one here. You can see that the ratio between the voltage and the current remains the same. And if that's the case, then resistance is therefore going to be the same. In fact, if we know that resistance is equal to voltage divided by current, and in this graph, you can see voltage is the y-axis and current is the x-axis. That means that resistance would be the rise over the run. So by determining the gradient of this graph, we can actually determine what the resistance of this conductor is. But that only works because the resistance is staying the same throughout. You can see it's a straight line. That gradient does not change. But if we have a device, say a light bulb or something, where we increase that voltage, but we find that the current doesn't increase proportionally with it. So in this particular graph, as we increase that voltage, the current gets to a point where it plateaus. So the current does not increase anywhere near as much as the voltage increases. So then this equation here, although we can still use it to determine the instantaneous resistance, like the resistance at that particular point, it's not ohmic because it doesn't follow that ratio at all points. In other words, the resistance is not constant. So if the resistance is constant for all different voltages and currents, then we say it's ohmic. And if it's not constant, in other words, if the resistance changes, that ratio doesn't exist for all different voltages and currents, then we say it's non-ohmic. All right, so in this demonstration, we are looking at Ohm's law. So what I've got over here is a power supply, and this is the rheostat. This is to allow me to finely tune what this power supply is providing. So effectively, this part here gives me a voltage that I can select, and then it's going to be coming around through this resistor, and then once it goes through the resistor, it's going to be going through the ammeter, and then back to the power supply. So effectively, this circuit is just a power supply going through a resistor with current being measured and going back to the power supply. Now, what I've got here is a way for me to measure the potential drop or the voltage across these two terminals here. So you can see at the moment it's 0 and there's 0 current running. So if I turn the power on, right, so what you see straight away is that the voltage is 1.98. I'm going to see if I can turn that up just to make sure it's perfect. So close enough, 2.01, and in response you can see the current is 0.2 amps. Now that is because the resistor that I've got is supposedly 10 ohms. So if you know that V equals IR, so the current is 0.2, the R is 10, so 0.2 times 10 is 2, which is what you're reading there. So everything at the moment is working really well. So when we look at Ohm's law, so if something is obeying Ohm's law, or if something is ohmic, like a resistor, it means that as I increase the voltage, so you can see here I'm increasing it, let's go to 3 volts. Actually, let's see if we can double it. We'll double it to 4 volts. So if I double that current, what you should notice is that, if I double the voltage, you should notice that the current doubles as well. So that would mean that this resistor, this device right here, is ohmic because it's obeying Ohm's law. So now let's try and look at something that isn't ohmic. All right, so what I've got set up now is a light bulb, and you can see the light is going up. So it's no longer a resistor. It's the exact same setup, but I've now got a light bulb. So I've given it 2 volts, and the current going through it is 0.16 amps, which means that if I double this voltage, then I should get 0.32 amps. So let's see what happens. So I've gone to 4.1 amps and it's 0.23 amps. So you can see that the amount of current going through the circuit is not proportional to the voltage because I've doubled that voltage and it is not, I have not doubled the current. So for me to get the same amount of current as I was expecting, so 0.32, so if I wanted to double the current going through that light bulb, I need to get to 0.32. Okay, and you can see that I need to give it 7 volts. So effectively, I'm more than tripling the voltage just to double the current. So it's no longer that linear relationship that Ohm's law gives us. So that's a demonstration of Ohm's law. And an example of devices that aren't ohmic is essentially anything that sort of has transistors involved, things like lights and LEDs. So for example, in an LED, you actually need to reach a certain voltage before any current flows at all. And then once you reach that voltage, that threshold voltage or the activation voltage, then you start getting something that resembles an ohmic curve, but overall it's not considered to be ohmic. And finally, I just want to talk about superconductors. So we talked about how temperature affects resistance. So if we lower the resistance enough in certain materials, we can get it so that the resistance of a component is effectively 0. And what this means is that the electrons, if they're circulating through that substance, they will circulate without any resistance and they will not slow down. Now, when you have that sort of feature, you have some very, very interesting electrical and especially magnetic properties. And that's where you have sort of your magnetic levitation and all those really interesting things happening. Now, although superconductors won't be part of what we do for the next few weeks, we're going to be looking at regular circuit components. That's actually a really interesting field if you want to get into that. Okay, and that's it for this presentation. So now that we've got these basic things sussed, we can start looking at analyzing circuits. And that's when things get really interesting.